Okay, this is going to be our third video on magnetic fields and magnetic forces. In this video, we're going to be covering two sections. We're going to cover section 27.4 and section 27.5. Section 27.4 is sort of all about one interesting result that we can pull out of our magnetic force equation. Definitely something worth looking at, and something that we could sort of use to answer questions in the future. Section 27.5 looks at some applications of that that equation, that F equals QV cross B, and sort of talks about some of the sort of devices you might see in a lab or in practice out in the field that you might actually use some of these principles, or at least the devices use those principles to actually function. So we'll take a look at both of those. We'll do a couple of quick examples, and we'll move on to the next one. Okay, so let's get started. For the video here, we're going to start off with 27.4, which is motion of charged particles in a magnetic field. And so we're going to consider a particle of charge Q moving in a magnetic field, which is given by our vector field B. It's going to be acted on by a force that we talked about in the first video. So we're going to have this magnetic force F equals Q V cross B. And now we want to consider sort of what's going to happen as this particle with a constant velocity, or at least a constant magnitude to its velocity, moves through our uniform magnetic field. And we sort of have the drawing here in figure A. Okay, and so we're given, let's say we're given F, V, and B. So we see F, V, and B here. We see that our B are these little crosses, right? So we're meant to imagine that our B is basically going straight into the page. Our magnetic field goes directly into the page. Our V is changing at a number of different points. We're going to be looking at this thing at point O, at point P, and point S. We're going to see how it changes as it moves around. And we're going to look at the force that this magnetic field exerts on our charged particle as it moves through these different points. And it's kind of going to lead us to this idea that our particle with constant magnitude to its velocity is going to be moving in a uniform in uniform circular motion here in this circular path that we see here of radius big R. Okay. And so if we look at this, we see that in all cases our velocity vector V is going to be perpendicular to our magnetic field, right? The velocity V lives in the plane of the page, and the magnetic field is perpendicular to that plane, pointing inward to the page. Okay, and so at all points, the magnitude of our force is going to be equal to F is going to be equal to QVB, right? Because the cross product is going to pick up only the part of V. And it's all of V because V is perpendicular to B. It's going to pick up all of that V contribution, and so we don't have to worry about the cross product because we can just pull. Well, I mean, for direction we would have to worry about it, but the direction is always going to be in the direction we have pointing on the page here. So our magnitude we can just pull out of this equation here. Okay. And so if we have velocities which are slowly turning in this way, and we have forces that are always pointing radially inward, this sort of leads us to this sort of circular path, right? Our velocity is always going to have the same magnitude, and that's because our V, or the magnitude of our V, like not the vector V but the speed, is never going to change because B being perpendicular to it means that B can never do work on the particle. And so V is only going to change in direction. It's not going to change in magnitude. Okay, and so again, this leads us to this uniform circular motion that we see here. Okay, and the whole idea of uniform circular motion, and maybe before I say that, I should point out what the second diagram is. The second diagram is actually this happening in practice. We do have these at the labs, or something similar to this in the labs at UFV. I'm not sure if they do this demo for you guys in first year, but maybe this year or maybe in the future you guys will see these really cool sort of electron beams that we just bend with magnetic fields. You can kind of see them. You can see this sort of glowing ring here is just a beam of electrons that's being bent into a circular path by these large coils here that are generating a magnetic field. This is exactly what's happening here, right? And you may see them in the lab, or you may not this year. I'm not sure if they do them for 112. But so when I mentioned uniform circular motion, which is what's happening here, this should sort of ring a bell from Physics 111. So if we remember, with a constant v and a fixed radius, our centripetal acceleration is going to be defined as this value that we see here. So a centripetal or a sub c, or depending on how you guys would have defined it in your 111 class, depending on who your prof was, you're going to end up with this expression on the right hand side. So v squared over r. Okay. And since the magnetic forces are the only forces that are acting, we can sort of just apply Newton's second law to this, and so we end up with, well, this is our force, right? And our force is going to be equal to mass times acceleration. So we have mass times the centripetal acceleration. That's just this times mass, so that gives us this right-hand expression. And this middle expression here, that's just our force from above, right? We said that that's going to be the magnitude of the force, because v is always perpendicular to b, right? And so we end up with this expression, and with this expression we can rearrange things and solve for r, right? So we can get this circular path, and we can see what r depends on. R is going to depend on the mass of the particle. R is going to depend on the velocity of the particle. And again, this is the velocity. It's going to be perpendicular to the field, right? Because we made that simplification above. It's going to depend on the magnitude of the charge. And if we had picked up a minus sign here, it's just going to mean that this particle is going to rotate in the opposite direction. So here we have this counterclockwise rotation. If it picked up a minus sign, it would rotate clockwise. And it's also going to depend on the magnitude of our magnetic field B here. Okay. We can use some more of these ideas from Physics 111. We can find what the angular speed, or I guess angular velocity, but angular speed in this case would be. If we remember back, our omega is our angular speed, and it's going to be equal to v over r. And so we can simply substitute in the r value that we had above here with our v, do some simplification, and we end up with this expression here. So our angular speed is simply going to be equal to the magnitude of our charge times our magnetic field over our mass. Okay. And so, I mean, this is directly pulled out of the force equation here, right? This is all stuff that just by sort of looking at this and thinking about it, we could sort of generate. But it's worth going over and looking at, because it's a kind of special case that really has some pretty interesting implications. We can see some cool sort of stuff in the lab from it, and we can also use it to make some interesting things happen in the lab, and do some experiments that we couldn't do if this wasn't a thing, right? So let's take a look at what happens if the initial velocity of our charged particle is not perpendicular to the magnetic field, right? So we have some component, and this is a diagram of what's going to end up happening. So we have some component of that velocity that is actually parallel to the magnetic field, and some other component of it, the majority of it in this case, is perpendicular to the magnetic field. Well, you can see here sort of what ends up happening. The portion of the velocity that is perpendicular to the magnetic field goes into making it end up moving in this uniform circular motion, but the uniform circular motion is interrupted by this piece of the velocity pointing parallel to the magnetic field, and ends up moving our circle that would normally be being traced slowly upward along our magnetic field, along B. So we end up with these helix shapes traced out by these charged particles as they're traveling through the magnetic field. So you can imagine this particle is following the uniform circular motion, but it's also being dragged. You're also dragging that circular pattern, that circular trajectory along B as this whole thing is happening. So in the x direction here, right? And so this is really what you would end up getting if you had the particle, the right charge on the particle, the right type of magnetic field, you'd end up with this sort of trajectory being traced out. You could also end up with, obviously, much more complicated things, right? If your magnetic field is not uniform, then you can end up with things that look like some of these examples, or much worse, right? You can have very complicated magnetic fields that have all kinds of crazy stuff going on. But here are two sort of easy to see and kind of easy to imagine examples. You can imagine this first example is something you could do in the lab. You could set up two coils with a bunch of current running through them, which would set up a magnetic field that looks something like the blue lines that you can see here. And if you sent a charged particle, a positively charged particle with a magnetic field going in this direction down through the middle of this set of coils, you would end up with some motion that looked like this, right? So you'd end up with this helix that gets larger and smaller, and this is why we kind of end up calling this a magnetic bottle, right? It kind of entraps this charged particle in this sort of helix-like shape as it goes through the two coils. Okay, so this is one example of something that would be more complicated. Another example is the Earth itself, and the way it has these Van Allen belts. I'm not sure if you guys have seen them before. It's not super important that we understand exactly how that works for this course, but it is a nice way to sort of think about the Earth's magnetic field and how charged particles get trapped in the Earth's magnetic field. And this leads to the nice auroras that we can see in the north and south regions of the Earth if we look at the right time when we have charged particles from the sun hitting the Earth's magnetic field, right? So those are just two examples of slightly more complicated magnetic fields and how charged particles would interact with them. Okay, so we can now move on to section 27.5. In this section, we are going to be looking at sort of some devices and experiments that can be done using these ideas. So all of these ideas here, we're going to use magnetic fields. We're also going to use electric fields in some of them, and we're going to use them in interesting ways, sort of both at the same time, that let us do some interesting things, and they led to some very profound discoveries in the late 1800s that really shaped a lot of our understanding of physics going forward. And it also still plays an important role today in doing in some of the equipment that we use in physics and chemistry. So let's take a look at this really quickly. We're going to be taking a look at a velocity selector. So let's assume that we have some source of I don't know why I did this. Some source of charged particles. I can kind of get rid of that. Okay, so imagine that we have some source of charged particles, which is supplying us with charged particles moving with some unknown velocity. Okay, so let's look at the diagram below here. I'll scroll down a little bit. So we have some sort of source here. We can imagine there's charged particles flying off in every direction here with all kinds of different velocities. So both different speeds and both different directions, right? So they're going to be pointing in different directions. They'll have different magnitudes to their velocities. And then let's say that for whatever application, we want to be able to pick out particles that have a very specific speed and also a very specific direction, right? So let's say we only want particles moving at, 100 meters per second in this direction directly down this pipe here. So we can do that by using what's called a velocity selector here. Now we could certainly select for the direction alone by only putting a very small slit there, right? If we only put a tiny little slit here, obviously we would only be getting particles that are moving in the direction of this green arrow V. But we wouldn't know anything about the magnitude of that velocity, right? They could be moving very slowly or they could be moving very quickly. But if we set up this velocity selector that we have here, this velocity selector will select for the velocities that we want. And here's how it kind of does that, right? So what we have here is a setup where we have a positively charged plate on one side, negatively charged plate on the other, so we have an electric field set up pointing in this direction, right? So as the particle moves through here, it's going to feel a force from the electric field pushing it in this direction, right? So it'll tend to crash into the negative plate. But there's also a magnetic field going sort of into the page. Obviously it wouldn't be into the page if it was actually a physical detector, it would be sort of perpendicular to the direction of the page, or to the plane of the page. And so because we have this magnetic field pointing in that direction and our velocity pointing in this downward direction, if we were to apply the right-hand rule here, we would kind of place our fingers on V and want to curve them toward the direction of B. Well, we would see that there's going to be a magnetic force tending to push the particle toward the positive plate here, right? So the magnetic force is trying to smash the particle into the positive plate, the electric force is trying to smash the particle into the negative plate, and if these two forces balance perfectly, then the particle can just zip right through and it won't hit anything, right? If the electric force going this way and the magnetic force going this way balance perfectly, particle goes right through. But the magnitude of the magnetic force depends directly on the velocity, right? So we can kind of turn that dial, and if we calibrate it just right, we can have both of these forces. You can kind of see it in part B here. We have the electric force going in this direction, magnetic force going in this direction, and it does depend directly on V, as we saw above, right? We saw in our equations up here that force is going to depend directly on the magnitude of our velocity. So if we tune it just right, these two forces will cancel exactly, and our particle is going to come squirting out the other side here, right? And so by tuning E and B, we get to select for what V we want to select for, right? Our V, because we need the two of these to be equal, we end up with this equation here. And so our velocity is going to be E over B, and so we can change the velocity by changing E or B, and then we make sure that we have this thing coming out at exactly the velocity that we want, right? So this whole setup is fairly simple, but it's kind of a very important tool that allows us to select the velocity of the charged particles that we want. Okay, so the textbook goes on to talk about J.J. Thomson and his EM experiment, which was held back in 1897. During this experiment, they did a bunch of work, and they ended up measuring the ratio of the charge of an electron to its mass. And from that experiment and some deductions that were made after the experiment, they were able to sort of show that there was such a thing as an electron, and this is sort of where we credit the discovery of the electron and really the sort of birth of modern particle physics, which is sort of the field that I work in, right? So this is really a sort of real milestone in moving physics into a more modern era, and it happened back in the very late 1800s here. It's a really interesting read, and I would suggest that anybody that's interested in going on in physics give that a quick read. But we're going to skip over it here. I just wanted to mention it really quickly. It is a section, sort of subsection in the textbook, but we'll skip it here to save some time. The experiment is basically just using one of these velocity selectors. Okay, so you can kind of read a little more about it if you're interested. The next thing we're going to look at, though, is a mass spectrometer, which is something that's used in physics and in chemistry quite a lot. And so what is a mass spectrometer? We're going to imagine that we have some source here, and this source could be something that we sort of turn into a source. You can imagine you have some sort of material here, and you, let's say you hit it with a laser, so you're kind of vaporizing some of its surface, and a bunch of ions are flying off that surface. And why are you doing this? Because you want to find out what this thing is made of, right? So you have a bunch of ions flying off the surface of this thing. What you end up doing then, if you want to see what the surface is made of, and you're using a mass spectrometer, you're going to set up a couple of slits in the front of it, so you're only allowing particles that are flying up in this direction to pass through. Then your charged particles are going to fly into a velocity selector. So this portion of our mass spectrometer is just a velocity selector from above, right? We're going to select out some velocity. It doesn't really matter what the velocity is as long as we're selecting a known velocity. If we know what the velocity is when this thing comes out, we're going to let it fly out of this end of our velocity selector into another magnetic field. It could be a magnetic field with the same magnitude and direction as our original magnetic field in the velocity selector, or a different magnetic field. Doesn't really matter. As long as we know what the new magnetic field magnitude and direction are, well, we know that these particles now, they no longer have an electric force balancing the magnetic force. So these particles are going to start to curl off to the side here. The larger the mass, we can see from this expression up over here, the larger the mass, the larger the radius of circle that this thing is going to make, and the larger the velocity. But we're controlling for velocity, so we'll know what the velocity is. The larger the velocity, the larger the sort of radius of these circles that this thing is going to make are, right? So we set up some detector here, and we can measure how far this radius is simply by measuring how far from the spout we have particles crashing into our detector. And so we can tell right away what the masses of these things are. And if we can tell the mass of an ion, and we know that it has some charge, right, because we've had it come through this thing and it's only going to work if it's charged in the right way, we can right away tell what those ions are. If we know the charge and the mass of an ion, we have a pretty good idea what that ion is, and we can tell what this original material was made of, right? And this is kind of a very simple sort of run through on the basics of what a certain type of mass spectrometer would work like. Okay. So that's all I really wanted to look at for those two chapters. Really, nothing super new here. Just we want to remember that this result is a thing that happens, and all this comes from this force equation that we talked about in the first video in this module. I'm going to do two quick examples here at the end. I believe, yeah, so there's one right here. We're going to do these two quick examples. They're both from the first section that we looked at here, so 27.4. And yeah, let's just work through these and see where they sort of lead us. So the first example, 27.3, is electron motion in a magnetron, right? So we have a magnetron. We could imagine this is inside a microwave oven. It's emitting electromagnetic waves with a frequency given to us here, so 2450 megahertz. And we want to know what the magnetic field strength is required for the electrons to move in circular paths with that frequency. Okay, so how would we sort of find this? Well, this is really just going to be using the equations from above and maybe a little bit of knowledge from our uniform circular motion in Physics 111. We should remember that our frequency is equal to our angular speed or angular velocity if it were a vector over 2 pi, right? So we can kind of rearrange this. We can get our angular speed is just going to be equal to 2 pi times our frequency. And we also from above, from what we discussed above, we know that our angular speed is going to be equal to the magnitude of our charge times the magnitude of our magnetic field over the mass of our particle. So we can, because both of these are equal to omega, we can equate these two sides. We're going to end up with Q B over M, M is equal to 2 pi F. And if we isolate B, we're going to end up with B is equal to 2 pi M F over magnitude Q. And at this point we have everything that we need. We simply need to look up what the charge and mass of our electrons are going to be. We know what the frequency is here, and so we can just substitute in numbers. This is going to end up being 2 pi times our mass, which you would need to look up or memorize. This would be in kilograms. And then we would have our frequency here in hertz, and so we end up with 2450 times 10 to the 6 seconds to the minus 1, right? And this is going to be over the magnitude of our charge, be 1.6 about times 10 to the minus 19 coulombs. And if you do the whole calculation, you're going to end up finding a magnetic field with a magnitude of 0.0877 Tesla. Okay, so that's the magnitude of the magnetic field that we would need to get this frequency of rotation. Okay, so that's that one. The next one's a little more involved. We have a little more going on here, and so what we're looking at here, this is 27.4. We're looking at a helical particle motion in a magnetic field. Okay, and so the problem starts off with in a situation like that shown in figure 27.18. Well, this is figure 27.18, what I put above from the textbook. And so we have a charged particle in motion, we have the charge of the particle, we have the mass of the particle. We're told that this uniform magnetic field, this uniform B field here, is half a Tesla. And we have the direction of the magnetic field pointing in the direction of the x-axis. Okay, so at t equals 0, the proton has a velocity given by these three expressions here. So we're given the x component of the velocity, the y component of the velocity, and the z component of the velocity. And so we want to find well, we're told that only magnetic forces are acting on this, and then at t equals 0, we want to find the force on the proton and its acceleration. And then in part B, we want to find the radius of the resulting helical path. We also want to find the angular speed of the proton and the pitch of the helix. Okay, and the pitch of the helix is just the distance traveled along the axis of the helix, right? So in a single period, how far is this, right? How far does it travel in a single period? Okay, so I have some numbers here, so we don't need to pull out a calculator, and let's take a look at this. So in part A, we're starting off. We're wanting to find what the force experienced by the. Am I going to have space here? Hopefully, by the particle is going to be. So we can right away write down our magnetic force equation. We know this is going to be F is equal to Q V cross B. We can just substitute in for what V is and for what B is, right? So we know that we still have Q. We're going to have Vx in the I hat direction plus Vz in the k hat direction. We have no V in the j hat direction because it's 0, right? So Vx is this value, Vz is this value over here, and this is going to be crossed into B I hat, right? B is pointing only in the I hat direction. So we still need to remember some stuff about cross products, right? So we have to remember that I cross I is equal to 0, but k, or k hat I should say, cross I hat is equal to j hat, right? So we're going to end up with this k hat and this I hat term crossing to give us some non-zero value, but this I hat and this I hat are going to cancel out. So this whole thing is going to clean up. It's going to end up giving us Q still remains, and we're going to have Vz, B in the j hat direction. Okay, and that's basically it. We just have to substitute in for what these values are. We have our Vz here. We have our B here. Q we have over here. And so if you substitute in those values, I won't rewrite it here, but you're going to end up with a force that is equal to 1.6 times 10 to the minus 14 newtons in the j hat direction. Okay, so that's the force that we end up with. Does this kind of make sense? Well, it does, right? Because we have to be careful about when we're thinking about this particle coming into this magnetic field, right? So we're looking at it right at the moment where we have some of the velocity pointing in the x direction, so that's not going to contribute to the uniform circular motion. There's nothing going on in the y direction. All of it is in the z direction. But if we think about what we think about getting if we cross everything going in the k hat direction with everything in the, well, everything, I mean the velocity is going in the k hat direction and the magnetic field is going in the I hat direction, so clearly the force needs to be in the j hat direction, right? Because it needs to be perpendicular to both. Those two unit vectors form a plane, and we need our force to be perpendicular to that plane. So this is exactly sort of what we would expect for that initial setup. We're also asked to find the acceleration at that initial time t0 for the particle here, and this is just a simple application of Newton's second law. F equals ma, which means that a is going to be equal to F over M. We just take the M that we're given up here, divide it through, and if you do that, you're going to end up with 9.58 times 10 to the 12 meters per second squared, again in the j hat direction, right? Because F points j hat, so A must point j hat, right? So this is our A. Okay, so that's the answer to part A. In part B, what are we looking for? We're looking for the radius, we're looking for the angular speed, and we're looking for the pitch. Okay, so the radius is not too bad, right? So we have this expression for the radius from above, but we have to remember that in this expression, this v is only picking up the v that is perpendicular to our b, right? So we're only picking up the part of the velocity that is not in the I hat direction. We only want parts that go like j hat or k hat. Well, we have no j hat here, right? And this velocity is not going to be changing in magnitude, so it's always going to be this magnitude. It'll change directions. The v will change directions as this thing spins around, but the magnitude will always be the same, and it'll always be equal to this, right? So this v is only going to be the v that is contributed from the k hat direction to begin with. And so really we end up with an expression that looks like this. It's going to be vz qb, okay? And we can just substitute in values for that again. This is going to end up being 1.67 times 10 to the minus 27. That's our mass. This is our vz. And in the basement, we're going to end up with our charge and our magnetic field is just 0.5 Tesla, right? If you were to do that calculation, you would end up finding that R is equal to 4.18 times 10 to the minus 3 meters. Okay, so that's the radius. That's the radius of this helix, right? So you can imagine like the radius of these loops. Okay. We're also looking for our angular speed, right? And this is pretty easy. Once we know the radius, we know the velocity in the direction that's going to be causing our uniform circular motion. Even though it's not really uniform circular motion, the portion of the motion that's like uniform circular motion is going to be our v here. So this is really just, again, going to be vz over r. We just calculated what r was, so this value would just come down here in the basement. We're going to end up with 4.18 times 10 to the minus 3, and our vz upstairs is 2 times 10 to the 5. If we do that calculation, we end up finding an omega equal to 4.79 times 10 to the 7 radians per second. Okay, so that is our angular speed. And then finally, we want to know what the pitch is. What the pitch is for this thing. So we want to know in each, as this thing does one full sort of circle, what is the distance between sort of each loop in this trajectory. Okay, so if we look at that, what we need to know really is what the time to do one loop would be, and then we can find what the distance traveled, because we know it's traveling in this x direction always at this constant speed. How much distance will have been traveled in the time it takes to do one loop, right? So we start off by trying to find what the period is. We know that the period from our earlier work in Physics 111 on uniform circular motion is going to be equal to this value here. We just calculated what omega was, so we can substitute in that. That's going to be 4.79 times 10 to the 7. Do the calculation, you're going to find 1.31 times 10 to the minus 7 seconds. So that's how much time it takes for this thing to do one loop, right? And how far up the x-axis is it going to travel in that time? Well, the pitch is going to be equal to our Vx, right? That's the velocity in the x direction, times the amount of time it takes to do one loop. And so we just put in those values. Our Vx is given to us. And we just put in our period here, right? Okay, and if you do that calculation, you're going to find the pitch is equal to 0.0197 meters. Okay, so that is the distance between each one of these loops. Okay, and so that's it for these two sections. In the next video, we will start looking at current and how current is going to interact with magnetic field. So I'll see you guys in that one.